Okay, welcome to Linear Functions Flip Lesson number 1. In class, we worked with the graph of a line, and we remembered to read our graphs from the left to the right, just like a book. And we learned a little trick. If we get confused whether a line is increasing or decreasing, we can sign our name on the line and go from there. We also worked with the rate of change, which is another way of saying slope. We talked about how to find corner points and how to find the rise, how to find the run, and what rate of change refers to. For today's lesson, we're going to be looking at the equation that matches with lines. The equation, when it's in this form, slope-intercept form, which don't worry about that right now, gives us the rate of change. The rate of change can always be found as the number in front of the x. You can double check looking at the graph and find rise over run to see that this equation matches with this line. The slope is the same. The rate of change is the same. So making a table is a good way to see what this equation is all about. And so if you remember making a table last year or in middle school, you picked easy numbers, right? We picked numbers like -1, 0, 1. We can do that because x is our independent variable, meaning we can pick any number we want. And then we go ahead and plug these numbers into our equation to see what y is. So if we want to know, hey, what's y equal to when x is equal to -1, we take the -1 and we plug it in for x. So in this case, we get y equals 3, plug in -1 for x, minus 2. Now, if you're good with math in your head, you probably didn't even need to write that. You could get the answer is -5. But if you want to double check yourself, you can always write it and then put this into the calculator, hit enter, and you get -5. So for this equation, we get -5 for y when x is equal to -1. So I wonder what y would be equal to when x is equal to 0. We could try doing this in our head, right? We could take 0 and plug it in for x. 3 times 0 is 0. 0 minus 2 is -2. You could also write it out and put it in the calculator. I wonder what y is equal to when x is equal to 1. So we're going to do the same thing. We're going to plug 1 in for x. 3 times 1 is 3. 3 minus 2 is 1. And if you want to double check, you can find these points on our line. So when I'm looking at -1 and -5, I know the point -1, -5 is right here on my line. If I'm looking for the point 0, -2, that point is right here on my line. 1, 1, that point is right here on my line. So we could have found the corner points on the line and wrote them in the table. But we don't need to do that because that's another way to make a table. So sorry about that. This is the way we normally make a table. A second way to make a table would be just to look at the graph itself, the line, and find the corner points which match up. Okay, so now we have a table that represents the line. It's not complete, right? It doesn't list all the points on this line because that would take forever. That would take the rest of our lives. So before we leave this slide, I want you to notice that we have an equation that matches this line, that matches this table. So we just noticed that the equation of a line reveals what the rate of change is when it's in this form, slope-intercept form. And so let's practice these. If you see the equation y equals 4x plus 10 and you're asked to find the rate of change, we know that the number that's in front of the x is the rate of change. If you're asked whether it's increasing, decreasing, or neither, what they're really asking you is, hey, is your rate of change positive? Because if it's a positive rate of change, it's going to be increasing, right? Okay. So go ahead and write down the equation y equals 7x minus 2. Where can we find the rate of change when an equation is in this form? That's right before the x. Since 7 is positive, that means that our slope is increasing, our rate of change is increasing. Go ahead and write down this equation, y equals negative 5x plus 8. Where can we find our rate of change when it's in slope-intercept form like this? Right there. Now, this rate of change is negative, and so that means that this line is going to be decreasing. Go ahead and write down this equation, y equals 1/2 x plus 7. Where can we find our rate of change? That's right, when it's in slope-intercept form, it is right before the x, so we'll put 1/2. 1/2 is a fraction, but it's still positive. So a positive rate of change always increases. So we're getting lots of good practice. Let's go ahead and write down this next equation, y equals x plus 3. All right, when we look at this equation, y equals x plus 3, what do we notice? There's no number in front of the x, right? And so when there's no number in front of the x, let's just stop for a second and talk about that. If there is a number like 2x, well, we know there's 2 x's, right? Or 5x means 5 x's. But then when there's just x alone, how many x's are there? 1. So when you don't see a number in front of the x, you know that number is 1. Rate of change then will be 1. 1 is a positive number, so it is increasing. Go ahead and write down this next one. It looks a little tricky, right? It's just short, y equals 8. Even though it looks different than the others, this is also in slope-intercept form. And I can hear you say, wait a minute, Ms. Overby, I don't see a slope. So here's the deal. You could rewrite it because you're right. We don't see an x, we don't see a slope. It's because the slope is 0. And if we have 0 x's, we don't write that down, right? It's kind of like saying, I have 0 money in my account. There's nothing there. So that's why they don't write it. You're not going to see the equation this way. You're going to see it this way. So we know that when the slope is missing, it's because it is 0. So our rate of change is 0. Okay, so let's think about this. 0 is neither positive nor negative, so that should give you an idea about what this answer is. That's one way to look at it. It's neither increasing nor decreasing because it's not positive and it's not negative. It's neither positive or negative, so it's neither increasing or decreasing. And think about if you're walking along and there's no slope involved in, let's say, the grass you're walking in. It's not sloping upwards, it's not sloping downwards, it's just flat. That is a rate of change of 0, where it's neither increasing nor decreasing. And let's look at this one. It's similar to this one over here in that we don't see anything in front of the x, but we do see a negative. Once again, it's really saying, you could say negative x, or you could say negative 1x, which means that its rate of change is negative 1. It is a negative number, and that means that the rate of change is decreasing. Okay, table of lines also show us the rate of change. Let's look at this first one that's on your sheet. There are 2 methods to finding the rate of change from a table. The first one is just to look at the pattern, and if we look at the y values, we see that 5, 7, 9, 11, 13. What's going on here? That's right, the y's are increasing by 2. The rate of change is a positive 2, so we would write 2 here. Since it's positive, it is increasing. The second method to do this is to look at the pattern itself and start with hoops. So hoops is just a second method that sometimes we actually have to use, so let's learn it. We'd start with the bottom number. We say 13 minus 11, 2. 11 minus 9, 2. And we can see that that's another way to just see the pattern of what's going on as we move down the y column. This next one, let's look and see if we can find the pattern just visually. When I look at 9 and 5, I know that it's decreasing, right? So we can even look at the table and know, wow, the y column is decreasing. We already know that answer right away. We're just looking at the y column right now. And we can also see, well, how to get from 9 to 5? Oh, I subtracted 4. Oh, I subtracted 4. So we can see our rate of change is going to be -4. If you didn't see that right away, do the hoops. Start with the bottom. -7 minus a -3. If I put that in my calculator, I get a -4. -3 minus 1 is -4, etc., etc. All right. Let's look at this and see if we notice something. Wow, this column, all the y's are 5. Okay, is it increasing? No. Is it decreasing? No. It's neither. So we can answer that one really quickly. The rate of change, you're going to look at it and go, Miss Overby, there's no change. Everything's the same. So when there's no rate of change, when the y values remain the same, what do you think it is? That's right, I'm hearing you through this video, it's 0. And if you had any questions about that, you could turn to the hoops and you would get 0. All right, let's look at this next table. Before we look at the pattern, we're going to notice that there isn't a pattern. So when we look at the y, column, how do we get from 4 to -1? Well, we would subtract 5, right? How do we get from -1 to -3? Uh-oh, not subtracting 5, so we don't see a pattern. And the reason why is this. We took for granted something. I didn't talk about it because I knew we'd talk about it with this fourth one. We never paid attention to the x column, right? But I want you to pay attention to it here. See how in this table the x's are increasing by 1? They're going up by 1. Same thing here. It's going 0, 1, 2. They're all, in these 3 tables that we did, all the x values are going up by 1, which meant that we could ignore the x column and just focus on the pattern in the y column. But with this, the x column is not increasing. All the x values are not increasing by 1. The first one goes from 0 to 5, and then 5 to 7. This is crazy. So what it means is we have to do the hoops with this one. So what we're going to do is we're going to do the hoops on the right. -11 minus a -6. That's going to be what? -5. Now -6 minus a -3 is -3. -3 minus -1 is -2. -1 minus 4 is -3. And we're like, uh-oh, no, this doesn't look good. That's because we have to do the left side now. We have to do the x's. 15 minus 10 is 5. 10 minus 7 is 3. 7 minus 5 is 2. 5 minus 0 is 5. Now you're looking at me going, Miss Overby, this doesn't even make any sense now. We've got crazy numbers on both sides of the column. Well, we need to remind ourselves what rate of change actually is. Rate of change is rise over run. And when you think about what the rise is the change in the y. We started at one point and we rose up. Anytime you rise or fall, that's the y in control. Anytime you run left or right, that's the x in control. So what we're going to do is use this idea that that rate of change is the change in y over the change in x. So let's see what that looks like. That looks like -5 over 5. Let's look over here, change in y over change in x. That's -3 over 3. Are these all equal to the same thing? -2 over 2. And, oops, 5 minus 0. What happened here? Oh, whoops. You probably noticed that I made a mistake here. So let's see, -1 minus 4 is -5, Miss Overby. Sometimes I'll make mistakes because I'm writing and talking at the same time. So -5/5 is also the same thing. They're all equal to -1, which is the rate of change, which is decreasing. Here are the linear equations we've worked with so far in this lesson. Do you notice the similarities in these linear equations? They are all in slope-intercept form, and we're going to learn a lot about slope-intercept form next unit. For right now, in your box that you see on your notes, go ahead and just write slope-intercept form. Sometimes linear equations can look a bit different. They're going to look different, but they're still linear equations. So when we look at this first one, it's not in slope-intercept form. This form is called standard form. So go ahead in your square underneath 3x minus 4y equals 12, write standard form. This one is not in slope-intercept form. This form is called point-slope form. So if you can write that point-slope form in your square, you're going to have to write a little small. Sorry about that. And this one is not an official form at all, but it's still linear. We'd have to work with it to make it look a little bit better and fit one of the forms. We are going to work with these different types of linear forms next unit, so I want you to get used to that linear equations can look different. So linear word problems also have a certain look about them, and here's an example of one. Kyle could do 5 push-ups when he was 1 year old. Every year he can do 10 more push-ups than the year before. Okay, Kyle's pretty amazing. How many will Kyle be able to do when he is 20? So what makes this linear? Well, the amount of push-ups that Kyle can do are increasing by a constant rate, right? Every year they're increasing by 10. That's considered constant because the rate that it's increasing each year doesn't change. It remains constant. It's always 10, always 10. Is there a way we could check to make sure this problem is linear? Well, we could make a table. So let's consider this. Kyle's age would be the x value. You could just put x if you wanted. And the y column would be number of push-ups. So we could go ahead. Oh, my writing's terrible. So when he was 1, he could do 5 push-ups, right? When he's 2, how many push-ups can he do? That's right, 10 more. 10 plus 5 is 15. And when he's 3, he could do even 10 more. It's 25. So we could look at the table and go, oh, yeah, the pattern is linear because there's a constant rate of change of 10. So let's look at another one. You've got a gumball tree in your yard. It gives off 2,000 gumballs in the fall. Your mom feeds it a special formula that will reduce the gumballs by 100 each year. How many years will it take before there are no gumballs on the ground to step on? What makes this linear? Right in your box, it's a constant rate of change. All right, or it's a constant rate, right? The gumballs they're decreasing by 100 each year. To understand it more, if you wanted to, you could make a table where we would have a year and number of gumballs. In the beginning, before we even started this, oh my goodness, the tree had 2,000 gumballs. That's awful. But after a year, it's going to have 100 less, so that's 1,900. And in 2 years, it'd have another. It's going to take a while, isn't it, to get rid of these gumballs. But you could make a table and look at the table and say, oh, yeah, that's got a constant rate of change there. It's decreasing by 100. Thank you for joining me. We're going to practice these a lot. The flip lesson is that you come in with these notes so that you're ready in class to practice and do activities and have fun so that you can really solidify this learning. I will see you in class. Thank you very much for joining me.